Most people think of dimensions as directions: left, right, forward and back, up and down, and maybe time as well if we're feeling generous. This framing is comfortable because it preserves the idea that reality is fundamentally stable, and that higher dimensions are simply extensions of what we already know. But that assumption is completely wrong. In the next 30 minutes, you're going to question everything you thought you knew about the universe. With each new dimension that we explore, it'll become clearer to you that the physical laws that bind us are not universal. They're local, conditional, dependent on the fact that we're trapped in the third dimension. But let's not get ahead of ourselves now. To understand higher dimensions, we must first understand the most basic of them, the first and second dimensions. A one-dimensional world is a line. It has length, but nothing else. No width, no depth, no concept of around or beside. The only movement that exists is forward and backward. To trap a one-dimensional object, you only need two lines, one in front and the other behind. That alone completely traps the object. But a two-dimensional object can simply step to the left or the right to escape this prison. In two dimensions, we roughly start to see the world as we know it taking shape. Length and width forms a plane. You get shapes like squares and circles. The concepts of beside and around, they start to make sense. But depth is still missing, and that absence carries consequences that are easy to overlook when you don't think too deeply about them. In a two-dimensional world, nothing has an interior in the way that we understand it. Everything is defined by its outline. A body is not a volume, but it's a border. A creature sees only edges, never what lies within another being, no matter how close it gets. From inside that world, this feels normal. It's complete. It's sufficient. Up until something looks down on it. Now, a three-dimensional observer, like us, viewing a two-dimensional plane, instantly destroys this illusion of privacy. Every internal structure is visible at once: hearts, organs, mechanisms, all exposed without any resistance. There's no need to cut into these objects to see inside the creature, because inside and outside are not protected categories anymore. They were simply artifacts of limited perspective. This is the first truly unsettling lesson of dimensions. The way that our world works, we think of using force to invade, but when you start thinking in the level of dimensions, you don't need any kind of force. You can simply bypass all of those defense mechanisms. Think of it like trying to use a wall to stop a ghost. It'll simply just go through the wall like that resistance didn't exist in the first place. If a three-dimensional being turns the hat of a two-dimensional being over, there's now no way for that two-dimensional being to ever get that hat back in place. To make things more unsettling, a three-dimensional being could perform surgery on a two-dimensional creature without ever breaking its skin. The organs of the two-dimensional creature would simply disappear without any force or resistance. From the lower dimensional point of view, this would feel like magic or divine intervention or reality malfunctioning. The same logic then applies to imprisonment. So in two dimensions, drawing a square around a creature is a perfect prison. There's no up, no down. That boundary is absolute. But to a three-dimensional being, the prison isn't just broken, it's wholly irrelevant. One step over the line and everything is, well, non-existent. Nothing about the square has changed, by the way. The rules just stopped applying. And I want to be clear, this is not a metaphor. This is how dimensions work. Now, with that in mind, consider the uncomfortable implication. Our own sense of physical laws only feel absolute because we are trapped inside them. We live in three dimensions: length, width, depth. From this, we get volume and mass. This is the first dimension where knots can exist. A string can loop around itself without passing through itself. Constraints feel real here because there's no higher spatial direction available to resolve them. This is why three-dimensional problems feel permanent. A wall blocks you, a body confines you, a prison cell feels inescapable. Every solution that we imagine is still forced to obey the same geometry. And even in our futuristic fantasies, they reveal this limitation. What's the most futuristic mode of transport that you can think of? A lot of you, I'm going to guess, said flying cars, right? It's what comes to my mind first. That alone reveals the fundamental limitations of only thinking in 3 dimensions. Every futuristic form of transport we have is simply finding a way to bypass 2-dimensional congestion by exploiting the 3rd dimension. Subways go under. Planes go over. All these different inventions do is bypass the 2-dimensional traffic. It doesn't free us from the limitations of time and space. So far, physics feels strict, but they're understandable. Everything has a physical limit that we cannot break, no matter how far ahead we think. However, this feeling completely falls apart once you start going higher. The 4th dimension arrives in 2 forms, and both are destabilizing. The first is time, and not time as the poetic passing of events that we conceptualize it to be, but as a coordinate. In this understanding, you don't simply exist somewhere, you also exist sometime. And in a way, we already experience this dimension. A location without a time is meaningless to us. Meet me at the library is incomplete without at noon. Seen this way, you're not a body moving through time, you're a 4-dimensional object stretched across it, a world line. Your birth, every action you've ever taken, and your death are not events that you approach. They're locations on a structure you already occupy. You experience this structure one slice at a time, the way a 2-dimensional being would experience a 3-dimensional object passing through its plane. This alone quietly breaks our intuition about freedom. If time is a dimension, then your life isn't unfolding, it already exists as a shape. From start to finish, you are predefined. But the more disturbing interpretation of the 4th dimension is spatial. A 4th spatial dimension does to us exactly what we do to 2-dimensional worlds. A 4-dimensional observer wouldn't see your surface. They would see everything. Organs, blood flow, digestion, tumors, neural activity, your entire body exposed without any form of penetration. The same you can conduct surgery on a 2-dimensional object without any injuries is the same way a 4-dimensional object can on you. Now to you, this would feel like a violation without cause, a lawless intrusion. To them, it would feel as trivial as placing your finger in the middle of a circle. If a 4-dimensional object entered our world, we would not perceive it as a whole object. We would only be able to observe its cross-sections, a point appearing from nothing and disappearing from nowhere, growing into a sphere, shrinking, vanishing, a ghost, not because it's transparent, but because it's incomplete. At this level, physics don't explode yet, but it does give us a glimpse. It shows us that everything that we think is protected on a fundamental level simply isn't. Now, the 4th dimension doesn't feel dangerous at first. It feels abstract. It almost feels philosophical. It's something you can gesture towards without letting it touch you. But abstraction is only a shield until the structure begins to assert itself. Once you follow the consequences instead of the metaphor, the 4th dimension becomes the point where physics stops acting like a barrier and starts behaving like a suggestion. In 3 dimensions, knots are permanent. They are a physical fact. A string can trap itself. A constraint forms because there is no available direction for escape, and this is why our headphones getting tangled feels so frustrating. The problem isn't the string itself, it's the space. The moment you introduce a 4th spatial dimension, knots lose their meaning. A knotted shoelace lifted into 4 dimensions simply slides around itself and falls apart. Nothing is breaking, you're not cutting the string. The knot just doesn't resist. It never truly existed. It was just an illusion created by insufficient room for it to explore. And this is a recurring pattern in higher dimensions. What feels like structure from below turns out to be congestion, a limit of space, and not an impossibility. This is why certain objects cannot exist properly in our universe. Take the Klein bottle, for example. In 3 dimensions, it looks like a bottle that intersects itself as if it were carelessly designed, but in 4 dimensions, it doesn't intersect at all. It has no inside and no outside. The contradiction isn't in the objects, it's in the space that we're forcing them into. When mathematicians draw a Klein bottle in 3 dimensions, they're not showing you what it is. They're showing you what happens when something real is crushed into an insufficient world. And this matters because it hints at something that is deeply unsettling. Reality, as we know it, may be full of objects and processes that only look paradoxical because we're seeing broken projections of them and not the full thing. By the time we reach the 5th dimension, physics begin to betray its own assumptions. In the 1920s, Theodor Kaluza rewrote Einstein's equations of gravity using 5 dimensions instead of 4. This mathematical experiment was designed to ask one simple question. What would happen if space-time had one more spatial direction? The result was unexpected and deeply uncomfortable. The equations split cleanly into 2 parts. One part described gravity exactly as Einstein had formulated it. The other part described electromagnetism with perfect precision. Light, magnetism, electric fields, all of it emerged automatically. In 5 dimensions, electromagnetism is not a separate force, it's geometry. This means something profound and very difficult to sit with. Light may not be fundamental. It may be a vibration in a direction that we can't access, a ripple in a dimension that we don't experience. From our perspective, gravity and light feel distinct because we are confined to a slice of reality that fractures them apart. However, from 5 dimensions, they could very well be the same phenomenon, just viewed from different angles. At this point, physics stops feeling like a set of rules and starts feeling like a shadow. Geometry also begins behaving strangely here. As dimensions increase from 1 to 5, the volume of a unit sphere grows. Space becomes more generous. The sphere reaches its maximum volume in the 5th dimension, and this is the peak, the moment where space is the most efficient at containing things. Then, something breaks. At 6 dimensions, volume starts to shrink. Now, this is counterintuitive in a way that cannot be visualized. You are adding more room, and yet objects occupy less of it. Spheres become smaller relative to the space that they inhabit. Packing becomes inefficient, and distance itself loses meaning. This is the point where string theory becomes unavoidable. String theory is often framed as speculative, but mathematically it's an act of desperation. When physicists try to unify quantum mechanics and gravity, the equations just refuse to behave. Probabilities stop adding up to 1 and the math collapses into nonsense. Unless the universe has 6 extra spatial dimensions, and not metaphorically, literally. These dimensions are not extended like ours. They're compact, curled into complex shapes known as Calabi-Yau manifolds. And these shapes aren't decorative. Their topology determines the properties of particles, mass, charge, interaction strength. The laws of physics may not be laws at all, they may be consequences of hidden geometry. So you change the shape, and you could very well change the universe. This introduces a deeply unsettling possibility. What we call the constants of nature may be environmental accidents, features of how space is folded rather than truths about reality itself. By now, intuition is useless. You can't picture 6 dimensions. I can't. Visualization fails because our brains evolved to navigate 3. What remains is just pattern recognition. And the pattern is clear. Higher dimensions do not add complexity evenly. They introduce zones of order and zones of collapse. And this much becomes undeniable in the 8th dimension. Now, dimensions 5 through 7 are mathematically messy. We don't know their exact sphere-packing limits. The geometry resists optimization. It feels chaotic. Then, suddenly, in 8 dimensions, certainty returns. Mathematicians know exactly how many spheres can touch a central sphere in 8 dimensions, 240, and that's not approximately, that's exactly 240. These spheres arrange themselves into a structure called an E8 lattice, a configuration so perfect it cannot be improved upon. This is not an abstract curiosity. The same structure appears in string theory, group theory, and error-correcting codes. The geometry of 8-dimensional space is so efficient that it helps modern technology recover lost information. Reality, at certain dimensional depths, becomes better at preserving order than we are. This raises an uncomfortable question. Why does structure suddenly decide, of its own volition, if it has that, to reappear here in the 8th dimension? Why does the universe seem to prefer certain dimensions? There is no answer yet. Only the implication that dimensionality is not neutral. Some dimensions support coherence, others erode it. Beyond this point, containment itself begins to fail. In 9 dimensions, a sphere placed inside a hypercube grows so large relative to the cube's corners that it begins touching edges that should be distant by our logic. By the 10th dimension, the sphere protrudes outside the cube entirely. This is not a mistake. The math is correct. A boundary no longer bounds. And yet, 10 dimensions are required for superstring theory to make sense at all. Without them, reality contradicts itself. At this level, physics does not break violently. It stops defending the idea that inside and outside are meaningful categories. And once that protection is gone, nothing we consider solid remains safe. Up to this point, higher dimensions have behaved like unfair advantages. They bypass walls, undo knots, merge forces. Even when geometry becomes strange, it still feels rule-bound, as if reality is playing a more complicated game, but remaining coherent. That illusion does not survive the next threshold. Beyond 10 dimensions, space stops behaving like a place where things can be meaningfully arranged. Optimization fails. Intuition dies completely. What remains is not chaos in the dramatic sense, but something colder. Indifference. One of the first signs of this appears in a phenomenon mathematicians call the sausage catastrophe. In lower dimensions, if you try to pack spheres efficiently, you cluster them. You stack oranges, you form lattices. Complexity improves efficiency, and this logic holds all the way up through familiar space and even into the moderately high dimensions. Then, at 42 dimensions, it breaks permanently. From dimension 42 onwards, it is mathematically proven that the most efficient way to pack spheres is not to cluster them at all. It's to line them up in a single endless chain. No matter how many spheres you add, no amount of clever arrangements beats a straight line. All higher dimensional cleverness collapses into monotony. This is not just unintuitive, it's intellectually humiliating. Every instinct about structure fails. Space no longer rewards complexity, it actively punishes it. And this matters, because it reveals something unsettling about high-dimensional reality. There are regimes where structure is not favored at all. Order does not emerge. It's suppressed. Before reaching that collapse, however, there is one last moment of almost supernatural elegance. Dimension 24. Like Dimension 8, 24 is a mathematical anomaly, a rare island of perfection in an otherwise turbulent dimensional sea. In 24 dimensions, spheres arrange themselves into the Leech lattice. One central sphere can be touched by exactly 196,560 others without overlap. This number is not approximate, it is exact. Even more unsettling is where this structure appears. The Leech lattice is not just theoretical, it's used in real-world error-correcting code. When information is transmitted through noisy channels, be it space probes, deep space communication, or digital storage, this 24-dimensional geometry helps recover meaning from corruption. In other words, information survives chaos because of a structure that exists far beyond our reality. And this reframes something fundamental. Perhaps higher dimensions are not where physics breaks, but where it's repaired. Perhaps the reason information feels conserved in our universe is not because of a law that we understand, but because deeper geometry refuses to let meaning fully dissolve. However, this is the last kindness. Beyond this point, dimensions stop feeling like scaffolding and start feeling like erasure. At sufficiently high dimensions, volume behaves in a way that openly contradicts containment. A hypersphere placed inside of a hypercube grows larger than the cube meant to contain it. The inside object becomes larger than its boundary. Containment fails in principle, not in practice. This is not poetry, by the way, it is literal mathematics. Some estimates place this inversion around hundreds of dimensions. The exact number is debated, but the implication is not. At extreme dimensionality, the very idea of a container collapses. Inside and outside lose their distinction. At this depth, geometry no longer respects borders. So how could such dimensions exist without tearing our universe apart? Well, because we're not immersed in them. They're compact, folded, hidden at scales too small to probe directly. Like a garden hose viewed from far away, higher dimensions collapse into invisibility when observed at insufficient resolution. To us, space looks three-dimensional because we cannot see the curvature wrapped inside of it. But invisibility does not mean irrelevance. If these dimensions exist, they can vibrate, and vibrations carry energy. In theories that include extra dimensions, these vibrations manifest as heavy, long-lived particles known as moduli. They are not part of everyday matter as we understand it. They are echoes of geometry, fluctuations in how space itself has been folded. For a very brief moment after the Big Bang, these moduli may have dominated the universe. Not matter, not radiation, but geometry. Space was ringing like a struck bell. They decayed quickly, but their decay may have left behind something quieter and harder to detect. Axions, ghostly particles that barely interact with matter. A background hum from dimensions we can't enter, but may still be able to hear. This suggests something deeply unsettling. The early universe may have been governed by dimensions we no longer inhabit. Our current reality may be the cooled, collapsed residue of a higher dimensional phase. Physics, as we know it, may be what survives after geometry settles into a simpler form. Seen this way, our universe is not fundamental. It's stabilized. This reframes what it means for physics to break. It doesn't shatter like glass. It thins. Assumptions lose their grip. Rules fade as soon as the dimensional context changes. From the perspective of higher space, nothing we experience is violated. It is simply local, and locality is fragile. Every time we climb a dimension, what once felt impossible becomes trivial. Walls become lines, knots become illusions, forces merge, boundaries fail, optimization collapses. At the highest levels, space does not feel hostile, it feels uninterested. Which leaves one final question. If higher dimensions exist, and if our universe is merely a cross-section of something much larger, then what we call reality may not be a place at all, but a shadow cast by geometry we are not equipped to perceive. And shadows do not control the objects that cast them. By this point, dimensions have stripped space of its reliability. Walls no longer confine, shapes no longer contain. Order appears and disappears without warning. But there's one assumption still standing, quietly holding the whole structure together. That assumption is observation. Now, so far, we've treated dimensions as places, spaces where objects exist and geometry behaves badly. But at the highest levels, dimensions stop acting like environments and start acting like conditions under which reality becomes definite at all. This is where physics stops being just unsettling and starts becoming existential. In classical reality, observation is passive. You look at something, and it reveals what was already there. A coin lands heads or tails before you see it. A planet follows its orbit whether or not anyone is watching. This assumption feels so natural that it's rarely questioned. Quantum mechanics destroys that. At the quantum level, objects do not have definite properties until they are measured. An electron does not choose a position. It exists as a spread of possibilities, a wave of potential. Only when interaction occurs does reality collapse into a single outcome. Reality behaves as if it does not commit to a single state until it's forced to. This introduces a dimension that is not spatial, not temporal, but conditional. A dimension where what exists depends on what is known. The deeper you follow this, the more disturbing it becomes. Consider the double slit experiment. When particles are fired through slits without observation, they form an interference pattern, proof that each particle behaves like a wave, passing through both slits at once. The moment you measure which slit the particle goes through, the interference disappears. The particle behaves like a solid object. Nothing physical is touching the particle or acting on it differently, only the information is changing. This suggests that reality is not responding to force, it is responding to knowledge. At this point, the idea of dimensions as places breaks down. The system seems to care less about where things are and more about whether distinctions have been made. This reaches its breaking point in a thought experiment known as Wigner's friend. Imagine a scientist inside a sealed laboratory measuring a quantum particle. From their perspective, the particle collapses into a definite state. The experiment is complete. Reality has resolved. Now let's imagine another observer, outside the lab, who has not looked inside. From their perspective, the entire lab, the scientist, the notebook, the measuring device, and the particle, exists in a state of quantum superposition. The experiment for that second observer has not been resolved yet. Both perspectives are, surprisingly, mathematically valid. So where does the collapse actually happen? Is reality definite when the scientist observes it, or only when the outside observer opens the door? If both are correct, then reality does not have a single state. It has observer-dependent layers. And I want to clarify here, this is not philosophical speculation. Variations of this very paradox are being tested now experimentally. At this level, dimension is no longer about geometry. It is about who is allowed to say what is real. The unsettling implication is this: reality may not be globally consistent. It may only be locally coherent relative to observers embedded within it. Which means that what you experience as a stable world may be a cross-section, not just of higher space, but of a higher informational structure. And this reframes earlier dimensional violations in a new light. A four-dimensional being bypasses your walls because the walls were only constraints within your slice of reality. A higher dimensional observer may bypass your facts the same way. From above, contradiction disappears. This raises a very dangerous question. If reality collapses based on observation, then what qualifies as an observer? Is it consciousness? Measurement devices? Interaction itself? Well, physics does not answer this cleanly. Different interpretations exist. Some say that consciousness matters. Others say it doesn't. Some claim all possibilities exist simultaneously, branching into separate universes. This leads to the many worlds interpretation. In many worlds, collapse never happens. Every possible outcome occurs, each in its own branch of reality. The universe splits continuously, fracturing into countless timelines. From this perspective, dimensions are not just directions, they're branches. You experience one path because your consciousness is embedded within it. Other versions of you exist elsewhere, making different choices, meeting different ends, and not metaphorically, literally. This introduces a dimension that cannot be traveled through, only inhabited, a dimension of outcomes. The unsettling part is not that many worlds exist, it's that from your perspective they're invisible. But from a higher vantage point, they may be equally real. Which brings us to the most uncomfortable possibility of all. Consciousness itself may be a low-dimensional phenomenon. It's not special, not central, simply trapped. If awareness arises from physical processes confined to a particular dimensional slice, then higher dimensional structures may not experience reality sequentially at all. They may not experience time as flow. They may not experience individuality as separation. To such entities, your entire life might be a static object, a pattern, a completed structure. This mirrors the earlier insight about world lines. You are not moving through time, you're stretching across it. Now, imagine a perspective where even that extension is visible all at once. From there, choice doesn't disappear, it simply stops feeling open-ended. This is why higher dimensions feel creepy. Not because they introduce monsters or chaos, but because they remove narrative. Cause and effect lose their emotional weight. Effort loses its drama. Becoming gives way to being. At the highest levels, physics does not describe events, it describes structure. And structure, well, it doesn't care how it feels to live inside of it. Which brings us to the final reframing. Perhaps the reason higher dimensions feel so hostile to intuition is not because they're alien, but because they reveal that intuition was never designed to survive truth at scale. Our minds evolved to navigate a narrow slice of reality where surfaces matter, time flows forward, and observation feels harmless. But beyond that slice, the universe does not become supernatural. It becomes honest. After walking through the highest dimensions, one question refuses to go away. If reality is this fragile, if walls are optional, time is a coordinate, forces are geometry, and observation shapes existence, then why does the universe feel so stable? Why does your body feel solid? Why does cause usually follow effect? Why does the world behave well enough for life to exist at all? And the answer isn't that higher dimensions are absent. It's that we are embedded too deeply in a narrow slice of them to notice their freedom. Stability is not a feature of the universe, it's a byproduct of confinement. Just as two-dimensional creatures would swear that lines are absolute and interiors don't exist, we swear that surfaces matter, that objects are sealed, that time flows forward, and that observation is harmless. These beliefs aren't wrong necessarily, they are locally correct. They hold only because we are trapped inside the same dimensional bottleneck. Every higher dimension we've explored reveals the same pattern. Rules do not fail everywhere at once. They fail only when viewed from above. Walls fail from the third dimension. Knots fail from the fourth. Forces merge in the fifth. Containment collapses beyond the 10th. Structure itself dissolves at extreme dimensionality. Yet, inside each layer, reality still feels complete. This is why physics appears stable to us, yet incomplete. It's not lying to us, it's speaking only about the part of reality we are allowed to inhabit. Now, this reframes the idea of physics breaking. Physics does not break when equations fail. It breaks when we ask them to apply outside their jurisdiction. The moment we demand global truth from local rules, paradoxes appear. This is why higher dimensions feel so disturbing to us. They expose that Everything we trust, causality, containment, individuality, is provisional, useful, but not fundamental. Even time, the axis we rely on to make sense of our lives, loses its authority at higher dimensional views. Past and future become positions, not processes. Change becomes geometry. From above, your entire life may exist as a static object, a structure with no privileged now, not unfolding, just there in its entirety. And this does not mean your experiences are meaningless. It means meaning is not created by sequence alone. And this is where the human discomfort peaks. Because if higher dimensions exist, then suffering, choice, effort, and identity are not erased, but they are recontextualized. They stop being the center of reality and become features of a particular slice. And that is the true source of the unease. We aren't disturbed by the idea of extra space. We are disturbed by the idea that we are not narratively central, that our struggles do not drive the universe forward, that our decisions do not shape reality globally, that our sense of becoming may be a local illusion inside a larger, already structured whole. And yet, I think at least, there is a strange relief hidden here. If higher dimensions reveal that reality is larger than our slice, then the fragility that we feel, it may not be personal. It may be structural. That anxiety that something is off with existence might not be a flaw in human psychology after all. It may be an accurate response to living inside a constrained projection. Our minds evolved to survive, not to see the full shape of reality. We never needed it to live day to day, which explains to us why higher dimensions feel so wrong. They don't threaten us with monsters or chaos. There is no Cthulhu waiting in the sixth dimension. They just threaten us with irrelevance. They suggest that the universe does not revolve around what we can perceive, measure, or narrate. That the deepest structure of existence operates at scales where our intuition just can't follow. And yet, we're here anyway. We move, we choose, we care. And perhaps that's the final paradox. Even if higher dimensions exist, even if reality is far stranger and colder than we imagine, experiences still happen locally. Meaning still arises inside slices. Consciousness still navigates its narrow corridor as if it were the whole. And maybe that's not a failure. Maybe it's the only way anything can feel real to us at all. Because a universe fully aware of its highest dimensions might be perfectly structured and completely unlivable. So, reality compromises. It hides its depth. It stabilizes surfaces. It enforces time. It protects identity. Not because these things are fundamental, but because without them, nothing inside that slice could survive. In that sense, physics does not break at higher dimensions. It lets go. And what remains is not chaos, but a quiet reminder that what we experience as reality is not the universe itself, but the version of it that allows us to exist. Which, depending on your point of view, may be the most beautiful or unsettling truth of all. Human beings measure progress in strange ways. We measure it in weapons, in skyscrapers, in GDP, in the number of social media followers that we've managed to accumulate. But if an alien civilization were observing us from across the galaxy, none of that would matter to them. They wouldn't care about our politics or our silly little social media platforms. They wouldn't care how quickly we can circumnavigate our planet or how fast we can get rage baited by a 12-year-old kid on Twitter. Because from a cosmic perspective, all of that is just noise. Instead, they would measure something far more fundamental, something universal, a metric that every civilization in the universe can be compared against. They would measure our energy. And when they did, what they would find would be so small, so inconsequential, that we might as well not even bother calling ourselves an advanced civilization at all. This is every level of cosmic civilizations and why humanity is still at the very bottom. In 1964, Russian astronomer Nikolai Kardashev proposed a brutally simple idea. If you want to know how advanced a civilization is, don't ask what it believes or how it measures itself. Ask instead how much energy it can control. Energy is the universal currency of existence. Every star burns it. Every planet absorbs it. Every living organism feeds on it. As a civilization grows, driven by curiosity, competition, fear, ambition, or even a mix of all of these, its hunger for energy expands, and that expansion can be measured. Kardashev used this measurement to divide potential civilizations into levels, Type 1, Type 2, Type 3. Each is defined by the scale of energy they could harness, but since then, futurists and physicists have extended the idea even further, imagining higher and higher forms of cosmic mastery, all the way to a theoretical Type 7 civilization. What begins as planetary engineering actually becomes the act of bending reality itself. And when you place humanity on that scale, the result can be humbling. Despite everything we have achieved as humans, from landing on the moon to counting the stars in billions of galaxies light years away, from launching satellites into orbit to splitting the atom and unleashing enormous amounts of energy, from pulling simple silicon out of the ground to building artificial intelligence that may one day cure diseases like cancer, we are still not even a Type 1 civilization. On the Kardashev scale, humanity sits at roughly Type 0.7, which means that in the grand hierarchy of possible cosmic civilizations, we haven't even reached the first level yet. Simply because we are still very limited in how much energy we can harness, control, and use. Specifically, most of our energy still comes from finite resources. We still burn dead plants to survive, coal, oil, gas, ancient sunlight compressed into a black liquid. Meanwhile, the sun bombards Earth with more energy in a single hour than humanity uses in an entire year, and we capture almost none of it. About 1/millionth of the sunlight that touches our planet is harnessed for use. The rest just scatters back into space, just wasted. From an interstellar perspective, we are nearly invisible. Our radio signals, which we once imagined would announce our presence to the galaxy, degrade into noise after just a few light years. A civilization even slightly more advanced than us would struggle to detect that we exist, and we have almost no control over our own environment. A supervolcano eruption could collapse our global civilization. A large asteroid could reset the entire experience of humanity just like that. A sufficiently destructive war could erase centuries of progress in just a few days, just a few missile launches. This fragility defines Type 0. A civilization that could be aware of the cosmos, but isn't in control of its own world. And yet, if we survive, we may not remain there for long. Scientists estimate that it would take humanity around 1 to 200 years to become a Type 1 civilization. But none of this will be easy. It will require great technical effort, but also incredible planetary cooperation, the likes of which we have never seen. To become Type 1, we must achieve planetary mastery. That means harnessing roughly 10 to the power of 16 watts of energy from renewable resources. It means building highly efficient global electrical systems, scalable fusion reactors, and advanced energy storage. But technology alone is not enough. The leap from Type 0 to Type 1 may be the most dangerous jump in the entire scale, because the same technologies that allow planetary mastery also allow for planetary destruction. Nuclear weapons, engineered pathogens, autonomous war systems, Environmental collapse. A lot of people believe that the shift from Type 0 to Type 1 is where the Great Filter occurs, a time period where civilizations either fully unify and stabilize, or completely destroy themselves before they have the opportunity to ever reach for the stars. If we were to pass through that filter, the world as we know it would look unrecognizable. A Type 1 civilization does not endure nature, it manages it. Weather systems could be monitored and adjusted in real time. Hurricanes weakened before they ever make landfall. Droughts eliminated through atmospheric engineering. Tectonic stress monitored to predict and potentially mitigate earthquakes. Energy would be captured from solar, wind, geothermal, tidal, and sources that we haven't yet invented, all coordinated by planetary-scale artificial intelligence systems. Cities would become fully integrated organisms. Transportation could rely on ultra-fast maglev networks connecting whole continents. Language barriers might dissolve into universal translators or even shared neural interfaces. A single planetary infrastructure could replace fragmented national grids. Medicine would radically extend our health spans, slowing or partially reversing aging. Diseases would become rare, genetic disorders corrected before birth. Global health systems, powered by AI diagnostics, capable of identifying illnesses before symptoms even become visible. From our perspective today, all of this sounds like science fiction, and in many ways it is. But what is remarkable is that none of it violates the known laws of physics. We're not talking about warping space-time yet, or traveling faster than light, or discovering an impossible material like vibranium or unobtainium or anything like that. All of these are simply logical extensions of technologies that already exist today. There is a reason that we are 0.7 and what we're describing is 1. It's not a far distance for us to travel. The problem is that even this small step requires something humanity has historically struggled with: the ability to see ourselves as all part of the same ecosystem. Right now, we divide ourselves into nations, ideologies, languages, and cultures. We compete over imaginary borders drawn on maps. We fight over resources on a single small world that from space looks like a fragile blue marble just floating about in the darkness. From the perspective of the ISS, all of these divisions simply don't exist, and yet we are holding on to them like they are absolute truths. If humanity is ever going to reach Type 1, it will require a major shift in perspective, a recognition that every person on this planet is ultimately sharing the same thinning atmosphere, the same rising sea levels, the same fragile biosphere, the same loss of biodiversity, the same pale blue dot. And if we can begin to act like this world is our shared home rather than a battlefield that we can plant flags on, then something remarkable may just happen. Humanity could take its first true step into the cosmic arena, because once a civilization achieves planetary mastery, it does not stop there. It would begin to expand. Permanent settlements on the moon, terraforming Mars, mining asteroids for rare elements. Humanity would no longer be trapped on a single fragile rock. We would become a multiplanetary species, still young, still vulnerable, but for the first time, no longer confined to our home. Yet even planetary mastery is still small compared to what comes next. A Type 2 civilization harnesses not the energy of a planet, but the energy of its entire star, roughly 10 to the power of 28 watts. To understand how enormous that number is, consider this. The sun produces more energy in a single second than humanity has generated in our entire history as a species. Every moment, our star releases a staggering flood of light and radiation into space, most of which simply disappears into the void. A Type 2 civilization would capture almost all of it. The defining symbol of this era is the Dyson sphere, or more realistically, a Dyson swarm. Instead of a single solid shell surrounding a star, which would be nearly impossible to construct, a Dyson swarm consists of billions or even trillions of solar collectors orbiting the star in carefully arranged trajectories. Each collector would capture a tiny fraction of the star's light, but together they would intercept a significant percentage of the total energy output from the star itself. From a distance, a star surrounded by a Dyson swarm might appear dimmer in visible light while glowing intensely in infrared radiation as the collectors absorb the star's energy and emit waste heat. To build such a structure would require engineering on a scale far, far beyond anything humanity has ever attempted or even conceived of. Entire planets might be dismantled for the raw materials for such a project. Asteroids stripped down to their elemental components. Mercury, for example, could be slowly broken apart and transformed into trillions of these orbiting structures. Automated factories would operate throughout the solar system, harvesting metals, assembling new components, and launching new collectors into orbit. Over centuries or millennia, the architecture of the entire solar system would slowly change. But the reward would be staggering. With stellar-level energy, many technologies that currently exist only in theory suddenly become possible. Matter-energy conversion becomes practical, allowing civilizations to convert mass directly into energy with incredible efficiency. Massive artificial habitats could be constructed in orbit around the sun, each capable of housing billions of inhabitants. Giant rotating rings or cylindrical megastructures could simulate gravity through rotation, creating artificial worlds floating out there in space. Planets themselves could be moved, orbits adjusted, asteroids redirected, entire planetary systems reshaped to optimize energy collection and long-term stability. A civilization with access to the full output of a star would effectively eliminate energy scarcity forever. And once energy becomes abundant, many of the limitations that define our current civilization begin to just disappear like that. Scarcity fades, it's gone. The competition over limited resources that has shaped much of human history instantly disappears. With enough energy, raw materials can be extracted from asteroids, synthesized from basic elements, or recycled indefinitely. Economies built around scarcity may evolve into something entirely new. At this stage, civilization itself may begin to transform into something fundamentally different from what we recognize today. Biology may no longer define the limits of our intelligence. Cybernetic augmentation could allow individuals to enhance their cognitive abilities far beyond natural human capacities. Advanced genetic engineering might allow bodies to be redesigned, optimized, or completely reimagined. Some individuals may choose to abandon biological forms altogether in favor of a digital consciousness. Those digital consciousnesses could allow minds to be transferred into computational substrates. Instead of living inside fragile biological bodies, consciousness might exist inside vast computational environments powered by stellar energy. Entire civilizations could live inside simulated worlds that feel as rich and detailed as physical reality, or perhaps maybe even more so. Individuals might move freely between physical and digital forms, one day inhabiting a biological body, the next existing entirely as information inside a virtual universe. Minds could be copied, backed up, or merged together to form collective gestalt intelligences. Identity at that point becomes fluid. The boundaries between individuals blur as consciousness becomes something that can be duplicated, shared, or expanded across multiple environments at once. Lifespans could stretch indefinitely as minds are preserved and restored whenever necessary. And yet, even with all of this unimaginable power, a Type 2 civilization still faces a fundamental limitation. It is bound to a single star, Stars, like all things in the universe, eventually die. Some collapse. Some expand into red giants that consume their inner planets. Some explode violently as supernovae, releasing enormous amounts of radiation that sterilize entire solar systems. For a civilization that has built its entire existence around one star, that vulnerability is unacceptable. And so, once again, expansion becomes inevitable. Because if a civilization can harness the energy of one star, well, the next logical step is obvious. Harness the energy of billions of them. A Type 3 civilization no longer thinks in terms of planets or even stars. It thinks in terms of galaxies. To reach this level, a civilization must command roughly 10 to the power of 36 watts of energy. That is the combined output of billions of stars. The entire Milky Way then becomes raw material. Every solar system becomes a node in a vast coordinated network. Every star is a power source. But how does a civilization expand across 100,000 light years? Well, the most widely imagined method is through self-replicating machines known as von Neumann probes. These probes would travel to nearby star systems, harvest local materials, build copies of themselves, and then send those copies outward again. Over millions of years, this wave of machines could spread through the entire galaxy, constructing Dyson swarms around star after star, linking them into a unified energetic web. From our perspective, this sounds like the ramblings of a madman, but on a cosmic timescale, it's almost inevitable. At Type 3, astroengineering becomes routine. Entire solar systems are rearranged for efficiency. Gas giants are dismantled. Stars may be star-lifted, their outer layers siphoned off and repurposed. Black holes are no longer objects of fear, but of utility. Rotating black holes can act as extraordinarily efficient power plants, converting matter into radiation with near-perfect efficiency. They may also serve as computational hubs, processing information at densities that we can barely comprehend. Computation itself becomes a central theme of existence. When energy is abundant, intelligence scales. A Type 3 civilization might convert vast portions of the galaxy into a computational substrate. Entire star systems transformed into thinking matter. Consciousness is no longer limited to biological brains, but distributed across light years of engineered structures. At this level, citizens might exist as cybernetic hybrids, superintelligent artificial entities, or purely informational lifeforms encoded in stable quantum systems. Travel across the galaxy would rely on near-light-speed vessels, suspended animation, or perhaps engineered wormholes if space-time can in fact be manipulated locally. Time dilation actually becomes a practical tool. Entire cultures may evolve at different subjective speeds depending on their computational environment. And death becomes optional. Minds are able to be backed up and restored, forked into parallel versions exploring different experiences. Some individuals may merge into collective intelligences, forming vast shared minds spanning multiple star systems. Others may choose isolation instead, carving out private realities for themselves, powered by a single star. But even a galaxy is finite. Beyond the Milky Way lies trillions of other galaxies, and the universe itself is expanding. If a civilization waits too long, distant galaxies will slip beyond the cosmic horizon, unreachable forever. So, a Type 3 civilization, if it's ambitious, has to think even bigger. And this is where we begin to enter purely speculative territory, because when Nikolai Kardashev first proposed his scale in 1964, this Point 3 is where it ended. A civilization that could harness the energy of its entire galaxy. Once we move past this point, we are stepping far beyond anything grounded in current engineering or even well-established physics. We're no longer talking about technologies we could realistically imagine building in the next few million years. And yet, Even though these levels may never exist, they still serve an interesting purpose, because thinking about them forces us to stretch our imagination to the absolute limits of what intelligence could one day become. It invites us to ask questions about the ultimate trajectory of civilization, consciousness, and the universe itself. In other words, if these civilizations say they never exist, they still help us understand just how far the journey could go. So, with that in mind, let's continue climbing the ladder. A Type 4 civilization would command the energy of an entire universe, not just one galaxy, countless galaxies. Roughly 10 to the power of 46 watts or more, depending on the size of the observable cosmos. Expansion would no longer be limited by individual stars, but by cosmological structure itself. At this stage, the line between physics and engineering disappears. A Type 4 civilization might learn to manipulate dark matter and dark energy, the mysterious components that make up most of the universe's mass and drive its accelerated expansion. If these forces can be understood, they may be able to be harnessed. Galactic clusters could be repositioned, cosmic expansion potentially slowed or redirected locally, entire regions of space-time optimized for energy extraction and computation. This is sometimes described as reality engineering. The fundamental constants of nature, the strength of gravity, the charge of the electron, the cosmological constant, might no longer be fixed parameters but adjustable settings. A sufficiently advanced civilization could experiment with new configurations of physics in isolated regions, testing alternate versions of reality. Beings at this level may not inhabit space in any traditional sense. A single consciousness could distribute itself across galaxies, experiencing billions of environments simultaneously. Individuality stretches to its breaking point. One entity might occupy countless bodies, physical and virtual, across multiple cosmic domains. At this point, survival is no longer the goal, it's something in the rearview mirror. Now exploration is our main focus. Yet, even this assumes that there is only one universe. If our cosmos is just one bubble in a vast multiverse, then a Type 4 civilization remains confined to a single bubble. And confinement is something advanced intelligence rarely tolerates. A Type 5 civilization would no longer be confined to a single universe. Instead, it would operate across the multiverse itself. Up to this point in the Kardashev ladder, every single step has simply been about scale. First, we mastered a planet, then a star, then an entire galaxy, eventually, perhaps, even the universe itself. But a Type 5 civilization takes a completely different step this time. Instead of expanding through space, it begins expanding through reality. Here, energy is no longer the only metric that matters. A Type 5 civilization has already surpassed the limits of a single cosmos. What defines their power now is their ability to move between, manipulate, and even design entire universes. The boundaries between realities then become permeable. Using what we might call meta-technology, this civilization could manipulate not just matter and space-time, but the deeper rules that define how a universe works in the first place. Parallel timelines, alternate physical constants, entirely different histories, all of these things become accessible to us. To understand this, it helps to imagine something more familiar to us. Think about how a programmer interacts with a computer. When a software engineer builds a complex program, they often create multiple instances of the same environment. One version might be used for testing new features, another for experimenting with radical changes, another for running simulations to see what happens if certain parameters are adjusted. Each environment runs separately with slightly different rules. but the programmer themselves can move between each of these programs freely. So imagine doing the same thing with entire universes. A Type 5 civilization could instantiate versions of itself in multiple realities simultaneously. In one universe, they might explore a cosmos where gravity is just slightly stronger, causing galaxies to form faster. In another, they might observe a universe where time behaves differently, perhaps flowing along more than one dimension. In another, entirely different particles could form the building blocks of matter. Each universe then becomes a kind of cosmic laboratory, a place to test ideas, a place to explore possibilities, a place to understand how different rules shape the emergence of complexity, stars, planets, and perhaps even life. And if one universe collapses, it hardly matters, because there are countless others. There is no death, at least not in the way that we would conceptualize it. If an individual consciousness exists across multiple realities at once, the destruction of one instance doesn't end the whole. It would be like closing a tab in a browser while dozens remain open. Imagine a piece of software that can run on any compatible machine. Now imagine a mind that can run in any compatible universe. Some beings at this stage might even act as what we could call cosmic gardeners. Just as humans plant seeds in fertile soil and watch ecosystems grow, a Type 5 civilization might seed simple forms of life in young universes. They might observe how evolution unfolds under different physical laws. In some universes, they may intervene, gently guiding development. In others, they may simply watch, allowing entirely new forms of intelligence to emerge on their own. In this sense, universes themselves become playgrounds. Different realities producing different forms of complexity, each shaped by the underlying rules of their predefined physics. And perhaps the most radical idea of all of this is that causality itself may no longer be fixed. To us, cause and effect feels like fundamental aspects of reality. The past always leads to the present always leads to the future. But if a civilization can navigate between timelines and universes, well, that chain may no longer be absolute. History itself could, ostensibly, become editable. Not unlike how we would edit a Word document. We write a paragraph, duplicate it, we change a few variables, and then we explore how the story unfolds differently with each new edit. A Type 5 civilization might do something similar with the entire timeline, branching histories and testing alternate outcomes, exploring what happens when small changes ripple outward across cosmic time. And yet, even this unimaginable level of power still implies a limitation. A Type 5 civilization can move between realities, but it is still operating within the system that allows realities to exist in the first place, which means there is another escalation. If there is a deeper layer beneath the multiverse, a set of meta-laws that govern how universes themselves emerge, then a Type 6 civilization would eventually reach it. Instead of navigating between realities, they would begin writing them. They wouldn't merely travel between universes. They would define the rules by which universes are possible in the first place. A helpful metaphor that helps me out is the relationship between a video game and the computer that's running the game. Characters inside the game can move through landscapes, build cities, and explore different environments, but they are still fundamentally operating within the rules that have been set by the game. The real power exists outside of the game, in the system running it. That's the hardware, the operating system, and ultimately the source code that determines what the game world can and cannot do. A Type 5 civilization might be able to jump between many different game worlds. A Type 6 civilization would be the one modifying the engine that runs them all. If universes are simulations, the Type 6 civilization has found the hardware. If universes are mathematical structures, they are able to edit the equations. If universes emerge from deeper meta-laws, they rewrite the source code that generates those laws. At this point, the word engineering almost stops making sense because engineering implies building something inside of an existing system. A Type 6 civilization would be operating on the system itself. Such a civilization would not merely create a universe with slightly different physical constants, they would define the framework that allows constants to exist at all. Imagine designing not just a virtual world, but the physics engine that determines how every possible world behaves. The rules governing gravity, time, and dimensionality would no longer be fixed properties of nature, they would just be design parameters. In our language, this begins to sound almost theological, but in principle, it may simply be the continuation of a pattern that intelligence has already been following for billions of years. Intelligence gains energy. Energy enables control, and control extends deeper and deeper. Humanity once shaped stone tools. Later, we shaped metals. Then we learned how to manipulate molecules. Now we manipulate information through computers and simulations. If that trajectory continues long enough, the next logical step is the ability to manipulate reality itself. Beings at this level may not resemble anything we would recognize as individuals. They may exist as patterns of pure information or as stable configurations within a vast meta-dimensional computational substrate. Emotion, suffering, and maybe even individuality could become optional parameters rather than fixed aspects of existence. At that level, science, philosophy, mathematics, and art would collapse into a single activity. Exploring the deepest possible structure of existence would be indistinguishable from creating new structures of existence. Discovering truth and creating truth might become the same act. To ask a question could be to generate a new universe in which that question is explored completely. And yet, even a Type 6 civilization still implies a boundary. There is still a distinction between the civilization and the total system it operates within. Even if it controls the framework of realities, it still exists inside some deeper structure, and that means there is still one final step left. A Type 7 civilization represents the theoretical endpoint of the Kardashev scale, not because it runs out of energy, but because it runs out of separation. Up until this point, every level of advancement has maintained a distinction between the observer and the universe being observed, between the creator and the creation, between the system and the one operating it. Type 7 erases that distinction entirely. At this level, there is no longer a meaningful boundary between civilization and reality itself. A Type 7 civilization doesn't live inside reality. It becomes indistinguishable from it. Energy, matter, information, space, time, and logic, they all collapse into a single unified structure. All dimensions, all timelines, all universes, and every possible configuration of existence becomes facets of one infinite system. The familiar concepts that structure our understanding of the world begin to dissolve. Location no longer has meaning because location only exists within particular physical systems. Time may lose its significance because time is simply a parameter within certain kinds of universes. What remains is something closer to absolute presence, an infinite generative structure capable of producing endless layers of reality. One way to ground this idea is through the experience of dreaming. When you dream at night, your mind generates an entire world. Landscapes appear, characters interact, and events unfold. The dream environment feels real while you are inside of it. But when you wake up, you realize something strange. The dream world and the dreamer were never truly separate. The dream existed inside the mind that created it. A Type 7 civilization might operate in a similar way. Reality itself becomes something like an infinite dream. Entire hierarchies of universes could unfold within a deeper structure of consciousness or computation. Such a system would appear indistinguishable from what we might call God. Not a deity in the mythological sense, but a foundational creative force. The generative engine from which all possible structures emerge, the ground of being itself. And this leads to a strange and slightly unsettling realization. If the Kardashev scale is even directionally correct, then intelligence, given enough time and survival, tends towards something that looks remarkably similar to godlike power. The difference between a cave-dwelling primate and a civilization capable of designing universes is not magic, it's simply time and energy compounded across billions or perhaps trillions of years. Which raises an important possibility. Either the universe is already filled with civilizations that reached these levels long ago, and we just can't perceive them because they operate on scales far beyond our detection, or almost no civilization survives long enough to reach them at all. And if that is the case, then humanity may still be facing the most important test in its entire history. Because before any species can become cosmic architects, it must first survive being a Type 0.7 civilization. And right now we are that Type 0.7 civilization. We argue on the internet. We burn fossil fuels. We divide ourselves into nations and ideologies. And yet, within a few centuries, if we don't destroy ourselves, we could become a planetary civilization. Within a few millennia, a stellar civilization. Within a few million years, perhaps something that begins to reshape the galaxy. It may sound insane, but think about it. The Milky Way itself is over 13 billion years old. On that timescale, we are barely even embryonic. If even one civilization in our galaxy achieved Type 3 millions of years ago, its engineering projects might already surround us, subtle or even invisible to our current instruments. Some scientists search for infrared signatures of Dyson swarms. Others scan for anomalies in starlight. And so far, we haven't found anything conclusive. This silence is known as the Fermi paradox. If the universe is so vast and so old, where is everybody? One answer is that higher-level civilizations are rare. Another is that they transcend physical form and become undetectable. Another interpretation is that we're just early to the party. That the universe is only just beginning to produce intelligence capable of climbing this scale. Or perhaps the final twist is this. Perhaps Type 7 has already been reached. Perhaps the reason the universe appears so finely tuned for complexity, for chemistry, for life, isn't random after all. Perhaps it's the interior of a higher order system, a simulation, an experiment, a garden, or simply a thought in a structure so vast that our entire observable cosmos is a minor fluctuation within it. If that were true, then we are not at the bottom of the ladder. We are inside it. And the real question is not how high civilizations can climb. The real question is whether we survive long enough to take the first real, non-simulated step.
In 1970, a British mathematician named John Conway created a project known as the Game of Life. Even though it's a game, it isn't one that you necessarily play. The Game of Life is a zero-player game, which doesn't make much sense when you hear it. The way it works is you put in a set of initial conditions and then observe. That's it. Once you put the initial conditions in, the game runs itself. Other than the small set of rules that the simulation follows, it runs on almost nothing. Some patterns only run for a few generations before they die out, while others seemingly go on forever. And this got me thinking, if a simulation as small as this, with very little variables, can result in something huge, what if we scale this up to, say, the size of a universe? A simulation that's more than just dots on a screen, but a simulation with galaxies, planets, and life. More importantly, if that is possible, how do we know that we aren't living in one of those simulations right now? At first, the argument for our universe being a simulation just sounds like complete nonsense. But when you actually take a look into it, it seems to become more and more plausible. How do you observe things? Well, you see them, or smell them, or observe them with any of your senses. This is your subjective reality, a reality based on a subject, you. You are alone in your own head. Everything that you observe or interact with ends its journey with neurons firing in your brain in a certain way to create your view of the world. With this being said, can you prove that there is an objective reality? That is, a reality that exists independently of our knowledge of it. A sort of overarching reality that encompasses all of our subjective realities. It exists without our observation of it. That sounds kinda confusing though. You can't know that an objective reality exists without someone or something to observe it. For example, if I went outside and stated that it was freezing, and you went outside and stated that it was scorching hot, that is where our subjective realities come into play. From this, it seems that two different minds, two different people, can observe a single object in multiple ways. In an objective reality, it would just be either freezing or just scorching, regardless of either one of our observations. In an objective reality, in order to prove something exists, you would have to observe it without observing it, which is an obvious contradiction. This kinda begs the question, can you prove that anything outside of your own mind is actually real? Babies aren't exactly the smartest things in the world, but they do give us a good insight into how we learn, how our minds develop, and how we become aware of the world around us. If you look outside your window, you might see a tree, or another house, or maybe your car in the driveway. But you don't need to physically look out there to know that those things exist. This is known as object permanence. It is the knowledge that objects exist even when we aren't perceiving them in any way. However, we aren't born with this skill. It's something that is developed over time. I'm sure you've seen or even played peekaboo with a baby before. When you cover your face, babies less than about a year old will believe that you disappeared into thin air. But when you take your hands away, you're back into their reality. The knowledge that things exist even when you can't observe them isn't learned until about 1.5 to 2 years into life. But is that actually true? This goes back to your subjective reality. Sure, after a while you might learn that some things seem to exist when we aren't observing them, but how can you be certain? At the end of the day, it is just your subjective reality. It's due to your consciousness that you can even observe anything. Take this for example. When you look at your computer or phone or television or whatever device you're watching this on, you know that all of those things are composed of atoms. But you can't really see them, can you? It's not until we take a device such as a microscope to observe them that we can actually see these atoms that make up everything. We can't see them until they're observed closely. So if this is true, this can make simulating a universe 1,000,000 times easier. Simulating an entire universe with billions of galaxies over billions of light years would take up a lot of computing power and would really just be a waste. All a post-human species would have to do is just simulate the consciousness of its subjects. Or maybe even subject. Is there any way to prove that anyone you talk to on a daily basis isn't just another function of code in the simulation? All the simulation has to do is just trick you into believing the world around you is real. When you play video games, you'll notice that things don't render in completely when you aren't looking at them. It's a waste of power and energy. Since video games are basically simulations of our own, why wouldn't a simulated universe follow a similar strategy? It's a very arrogant statement coming from a human, but hear me out. If a tree falls in the forest and no one is around to hear it, does it make a sound? It's a pretty popular psychological question, and it fits really well here. In a simulated universe, if no one is around or conscious of that even taking place, there's no reason for it to make a sound, or for the tree to even fall in the first place. If we stumbled upon that tree later on, it would just be lying on the ground to give the illusion that it fell. If we aren't observing galaxies in the Hubble Deep Field, what's the point of them existing in the simulation at all times? It could be possible that just bits and pieces of what we call the universe exist and are observed at a single time. If we look back at where technology was 100 years ago and compare it to now, you can see an obvious difference. If technology continues to advance at any rate that's greater than 0, then it is possible that in the future, whether it be 100 or 1,000,000 years, that we will eventually have technology with near unlimited computing power. But all I keep talking about is power and energy. How would a civilization even get this kind of power? Remember those creepy Russian dolls that when you open them up, there's another doll inside, and then another and another? There's a concept that's basically that, but on a stellar scale. Take our sun, for example. It's really big and really hot, and it radiates a ton of energy. If we could somehow harness all of that energy, we could use it to simulate millions of universes simultaneously. But how are we supposed to gather all that energy? Using a little something called Matryoshka brains. If an advanced civilization was able to build a megastructure encompassing the sun in multiple layers, just like the dolls, they would have all of the sun's energy at their disposal. A civilization capable of this could most likely do this with multiple stars, and thus will be able to simulate as many universes as they'd like. We can run simulations on our own computers that project our universe on a large scale. The Illustrious project does this very well. Just like the game of life, the project is much like a zero-player game. The scientists who created the project gave it certain properties that match our universe near the beginning and then just let it run. It's able to project our universe on a large scale very accurately, actually. And that's just with the computing power we have today. In the future, simulations like these will get more and more accurate until eventually, it may even be realistic. However, it cannot be perfect. When we observe atoms and attempt to view electrons or other particles, we cannot know both the position and momentum of these particles with 100% certainty. This is called the Heisenberg uncertainty principle. There's a limit to what we can know about the mass, energy, position, and time of a particle, meaning that in any simulation, there is no way to accurately represent everything exactly as it was. You can never truly have a perfect simulation of reality. It will always be slightly slower than the actual reality itself, even with an infinite amount of computational power at your disposal. In order to combat this, limits have to be put in place. Tricks and sleight of hand have to be used. A good example is this. If you have an old computer and try to run the newest games on it with 20 Google Chrome tabs open while also listening to music, you'll see an obvious decline in your computer's performance. The old computer doesn't have the computing power necessary to handle all of that strain, so it slows down. Now, think of black holes. When you're around that much matter in one place, that much information in one spot, time literally slows down. It's as if whoever created the simulation slowed down parts of the simulation to keep the energy required low. Could this be an explanation for the speed of light? Could this be the speed of computation of whatever simulation we may be in? There's no way to tell, and all of this is theoretical, and to be honest, insane. But it doesn't mean we shouldn't think about it. It could actually help answer some of the most sought out questions we ask. For example, the Fermi paradox. When we look out into the universe, we don't see any other signs of life. Are we really alone? Are we just a glitch in the simulation, or are we just not looking hard enough? Take the creatures that exist at the bottom of our oceans. Are they aware that we humans even exist? Are they aware of anything outside of their immediate vicinity? Do they know that they're living on a big rock floating around a hot ball of gas orbiting some big black hole of death in the center of the galaxy that sucks anything and everything in? Probably not. What if we're just like those creatures, but the furthest that we can observe or are aware of is what we call the observable universe? Perhaps the universe cannot exist without conscious minds to observe it. The idea of simulated universes could also explain the multiverse theory. The idea of a multiverse is just that, multiple universes, or perhaps infinite universes. In many situations, when there's a high chance of someone getting killed or someone has a near-death experience, they are reported to have said that their life flashed before their eyes. Their most special moments and memories from their life all comes rushing back to them in an instant. Researchers from Hadassah University in Jerusalem analyzed multiple cases of people who experienced these near-death experiences. In almost all of these cases, those being interviewed stated that they had lost all sense of time. One of them wrote, "There is not a linear progression, there is a lack of time limits. It was like being there for centuries. It happened all at once, or some experiences within my near-death experience were going on at the same time as others, though my human mind separates them into different events." Another respondent stated, "I could individually go into each person and feel the pain that they had in their life. I was allowed to see that part of them and feel for myself what they felt. When people experienced these things, it was as if they were living another life. They experienced things they never felt before. It was as if they stepped foot into an alternate reality. The idea of time didn't exist for a short while, and they were able to analyze things that no other living person could do." When you're talking with a friend and have that weird deja vu feeling that you've had the same conversation before, or that you've experienced exactly what they're feeling without actually having been through it. Perhaps you, in another universe or another simulation, actually had that same thing happen to you. The illusion of free will allows us to live our lives in any way we see fit. But what if every single decision that you've ever made has been pre-programmed into the simulation that we could exist in? Every decision you make branches you off into a parallel universe, a parallel simulation, where every choice that you have ever made has led you to this exact very moment. At home, on your phone, watching this very video. Current technology already greatly surpasses human performance and speed. That's why many big companies like Tesla use robots and other machines to do jobs that humans can't do as effectively. Biological neurons, those are the neurons that fire in your brain every second of the day, operate at a peak speed of about 200 Hz, whereas modern microprocessors operate at least 2 GHz, a whole 7 orders of magnitude faster. Even with modern technology, a super intelligent AI, for example, a human mind that runs on hardware faster than the brain, could make decisions millions of times faster than current humans would. It would be able to think of every outcome and pick from the best ones. However, we are not super intelligent AI. There is a limit to what the human brain can do, can observe. We have, though, made some very important discoveries that keep us asking questions. Most importantly, math. Math seems universal. There are numbers and patterns in things from the size of atoms to things the size of galaxies. Discoveries that we humans have made in only the past couple thousand years have allowed us to ask crazy questions like, are we living in a simulation? If we were to put every single one of the possible billions of simulations into a hat, jumbled them around and picked one out, what are the chances that we will grab the original one? The one who made all the simulations in the first place? What are the chances that the Earth we're living on even exists? Perhaps an advanced alien species came upon our dead planet after billions of years and found traces of our DNA, traces of our existence, and then made a simulation out of that to learn about the history of the barren wasteland of a planet they had just stumbled upon. If that's the case, then hello. We can never know for sure. All we can do is observe and hope that our game of life is one that we can win.
Meet Arthur. Arthur is really good at math, and he always has been. In fact, he planned on going to college to study math, but recently, life didn't pan out the way he expected it to, and so he's not quite where he thought he would be by now. Sounds like most of us. What is more probable? 1. That Arthur is a lifeguard at the local beach, or 2. That Arthur is a math tutor at a local school and a lifeguard in his free time. The correct answer here is 1, that Arthur is a lifeguard at the local beach, and only that. Now don't worry if you got it wrong, the majority of people do, even people with years of experience in statistics. If you chose 2, the error you made is known as a conjunction fallacy. You see, even without knowing anything else about Arthur beyond what the problem tells us, we can be certain that 2 is less probable than 1. Why? Because it's more specific, meaning it involves the probability of Arthur being a lifeguard and the probability of Arthur being a math tutor in conjunction. You may find it easier to visualize using a Venn diagram like this one. Questions like this one were developed in the 1980s to test cognitive biases, among other things. Why is this important for this video, though? Because it offers a general statistical insight that is relevant everywhere else as well, even, as you will see, in the deepest trenches of reality. The insight is simply that more specificity is less likely. The scenario of Arthur being a lifeguard and a math tutor may seem more likely, given how I've intentionally described Arthur to be mathematically inclined. But no matter how mathy he might sound, option 2 is the more specific scenario of the set, meaning more things have to go a certain way for it to occur, and it's therefore less likely. For a more drastic example, which is more likely? Getting struck by lightning, or getting struck by lightning and getting hit by a car in the same day? Now, onto the deepest trenches of reality. Have you ever wondered why most of the processes that go on in our lives are so seemingly irreversible? Why do they tend to go one way and not the other? Why is it that sugar can be stirred into a cup, but when you move your spoon the other way, it never unstirs itself? Why is it so that the sock drawer always needs to be organized by someone and never does so on its own accord? Why is it that a cup of cold water doesn't suddenly start boiling? These questions might seem unwarranted, and even dumb. We have so much intuition for these things that it almost seems unnecessary to ask these questions to begin with. But the reason why they need to be asked is because there's actually nothing in physics, no law or theory, that is against these processes reversing themselves. Laws that are obeyed when a cup of warm water cools down are obeyed just as well as when it heats up. So there must be something else that's tipping the balance almost. Something that almost wants gases to disperse through a room. Something that wants that cup to go cold. That thing is known as entropy, and it may have more to do with probability than with physics or chemistry. But first, let's try and understand what entropy means. You can understand a lot about a concept just by thinking about how it was named. The term entropy was coined in 1865 by Rudolf Clausius, who used it to define the second law of thermodynamics. However, it's much better if we try to understand the term using classical languages. The Greek word for entropy doesn't necessarily refer to disorder like you might expect. Rather, it talks about isotropic turning, meaning same no matter how you turn it. It's talking about the number of ways you can change something, or transform something, and still have it look the same. If you want to think of it in simpler ways, think of a disorganized desk. There are some ways in which you could organize a desk, and you can directly specify them, since an organized desk refers to a particular arrangement of things in a particular way. When it comes to a disorganized desk, there's really no rule that needs to be followed. A desk can be disorganized in so many more ways. Of course, a stash of papers on the left might look different than a stash of papers on the right, but in the grand scheme of things, it's simply disordered, especially when that's the only distinction you're drawing, one between order and disorder. Now, these things might seem simple enough, but there are certain missing links we need to address before we jump from an analogy like that to reality. First, let me remind you of what we just talked about at the start of the video, that more specificity is less likely. If we use that in the desk analogy, it means that since an organized desk is a comparatively more specific arrangement, it is less likely than a disorganized desk to occur just by random chance. I'm sure you have some intuition for this. If you organize your desk at the start of the week, unless you do something to maintain that order, it's probably not going to stay very ordered as the week goes on. Another missing link is the fact that in reality, things aren't super distinguishable. Particles at the atomic level are much harder to tell apart than the things on your desk. Even if certain disorganized versions of your desk might look different to you, you can rest assured that that won't be the case when you're looking at a million particles that all look the same. But arguably the biggest link that makes entropy a hard concept to digest is the scale of things. You and I really have no clue, and I mean it when I say it, no clue as to the real size and number of things. Of course, you've heard things about there being more stars than grains of sand and whatnot, but you really don't know how big it is. The term unfathomable gets thrown around quite a lot, but rarely is its use as fitting as it is now. Reality is unfathomably complicated. Even if you measure complexity just by the number of particles, you and I will fail to internalize the sheer size of things no matter how much we try. But I'm gonna go ahead and try anyways. Let's look at a box with 2 compartments and a few balls in them. Let's start nice and easy. So we have 2 identical balls. We allow the balls to move freely in between the 2 compartments. At any given point in time, where could the balls be? Well, they could all be in the left compartment, that's scenario number 1. Or one ball could be in the left and the other could be in the right. That accounts for 2 scenarios actually, since there's 2 the 4th and final scenario. All of these situations are equally likely. Now, what is the probability of finding both balls in the left compartment? Only 1 out of the 4 possible scenarios meets our requirement, so it's going to be 1 out of 4, or 25%. Now, let's bump it up a bit. Instead of having just 2 identical balls, let's have 4. Now, since there's more balls to move around, the number of ways they can be arranged also goes up. This can be represented by 2 to the power of the number of balls. In this case, 2 to the power of 4 is 16. Subsequently, our luck needs to be that much better to have all the balls spontaneously place themselves in the left compartment. And sure enough, the probability of having all 4 balls in the left compartment is now down to 1 in 16. Let's keep going. What happens when we have 5 balls? The probability goes down to 1 in 32. What happens with 16 balls? The probability goes down to 1 in 65,536. Notice how quickly the numbers jump up. Let's jump ahead a bit. What happens with 128 balls? Which is still a pretty good number, we can still kind of visualize that. The probability is now down to a staggering 1 in whatever this number is. Now let's take a step back to put things in perspective. We rarely have these well-defined compartments in reality. Things move around wherever they want to, and so the number of ways in which they can arrange themselves, even with 2 balls, is, and I'll say it again, unfathomably large. But that's still with just 2 balls. Remember earlier in the video I said it would be hard for you to distinguish between particles when you're looking at a million of them at once? Even a million particles is such a gross underestimation of reality, it's not even a contest. Something as little as 20 milliliters of water, basically the last sip of water in a bottle, has not a million particles, not 10 million, not even a quadrillion particles. It has over 10 sextillion, or 10 to the 23 particles. I'll spare you the math on this one, but let this be the takeaway. Things get really complicated really fast. To connect the dots with our other takeaway, in reality, an ordered arrangement of particles, such as gas that is not dispersed, or sugar that has not been mixed, also is significantly more specific when compared to other disorderly arrangements, like the desk example. That specificity makes it so much less likely. There's that many more particles to arrange, there's that much more luck needed for an orderly arrangement to exist. When you put all of that together, it starts making sense why things tend towards disorder. It's not so much that the laws of physics are biased towards one arrangement or another, rather, disordered arrangements are so overwhelmingly more likely than ordered arrangements, that if you let nature do its thing, things will always become more and more disordered. It's remarkable that, at the core of it all, it's not a law of physics or chemistry, but rather one of probability. Interestingly though, this can lead to the curious insight that it is indeed possible for a cup of water to spontaneously go from cold to hot. If the trend towards disorder is indeed independent of the laws of physics, there should be no problem with that happening. And in reality, there really isn't. Why don't we see it then? Well, the scale of things comes into play again. Going back to the ball compartment example, even if, say, we reduce the number of balls back to 1,000, and say that the balls change to a different arrangement a million times a second, we would still have to wait 300 quadro-nonagentillion years to see them all in the left compartment. That's many more orders of magnitude than the age of the universe, all for something as simple as 1,000 balls being put into a box. It's fair to say that it wouldn't be very wise to wait for that to happen. But what if you did? What if you saw out all of the arrangements of everything in the universe? Well, that brings us to the power of entropy and giving us an insight into the end of existence. You see, energy that we can use often needs to be in a particular form, in an ordered form. You can think of it in terms of food. Foods are just molecules, and everything has molecules. But you just can't eat everything. You can only eat things in which those molecules are arranged in very particular ways. In any other disordered arrangement, energy simply isn't very useful. And across the universe, energy is constantly transitioning from an ordered to a disordered form, causing a loss of useful energy. This sort of a progression also implies that at the start of the universe, energy was probably very ordered. But what must have got it there? Was it just a fortuitous ordering of particles? And what happens if this process keeps going on? Well, the most likely outcome is what is known as the heat death of the universe. As the arrow of time pushes us forward, each day the universe inches closer to maximum entropy, a state of no thermodynamic free energy. It doesn't necessarily mean that the universe will be hot or that it'll be cold. It just means that once everything has equalized to disorder, there will be no temperature difference to motivate a thermodynamic process to occur. Nothing changes. Nothing happens. Time ceases to have any meaning. This gradual process is inevitable, but it is nonetheless hard to see. The universe is hardly distinguishable from one day to the next, so to imagine that it might all one day simply cease to exist is a bit hard to wrap your head around. But that's not to say that we're so oblivious to the regularity of decay. It's all around us. Fading memories, aging, death, and the ultimate impermanence of our existence repeatedly remind us of decay. But if it's all so inevitable, what's really the point of it all? why even bother? In his book Enlightenment Now, Steven Pinker says, "The second law of thermodynamics defines the ultimate purpose of life, mind, and human striving: to deploy energy and information to fight back the tide of entropy, and carve out refuges of beneficial order. An underappreciation of the inherent tendency towards disorder, and a failure to appreciate the precious niches of order we carve out, are a major source of human folly." Maybe it really is just that. Small moments of apparent order against an inescapable reality of decay. But eventually, the lights have to go out one last time. The heat death of the universe is still a theory. It's a theory in a sense that we would have to cycle through all the different ways in which things can arrange themselves. And while the sheer numbers and timescales involved are too large for a human lifetime, that's not the case for the universe. The universe has time, and in a sense, is time. What is to say that in doing so, and going through all the different combinations, we won't stumble upon an orderly arrangement again? Sure, it might take many quadrannonagintillion years for something like that to happen, but it can happen. The possibility is vanishingly small, but it remains non-zero. And when that does happen, the lights just might turn back on. And for all we know, we might just end up back at square one.
The universe was really small and dense at one point, and then all of a sudden it wasn't. But wait a minute. Let's rewind and figure out what happened right here. This is because of two things: entropy and dark energy. To put it simply, entropy is the measure of order in the universe. It's a measure of uncertainty or randomness. The higher the entropy, the more disorderly the universe is. It's like your bedroom. A messy room is a high entropy state because it's much harder for you to be certain of where any specific object could be. For example, that sock you lost last week. But once you clean everything up and make it neat and orderly, it's much easier to be certain about where an object will be. This is entropy in a simple nutshell. But why is it important? Simply put, it could be what causes the end of our universe. Before we get to the end of the universe, we need to discuss what events will occur between now and then. This video is much like a sequel to a video I made recently called What Will Happen in 1 Billion Years. If you haven't seen it, I suggest you watch it. If you do, this video will make more sense. Anyway, right now, the Milky Way galaxy and the Andromeda galaxy, the closest galaxy to our own, are racing towards each other at a speed of about 110 kilometers per second. But in 4 billion years, the night sky will look the most beautiful that it has ever been. The collision of galaxies sounds like a really big threat, but actually our solar system will most likely remain intact. Due to the huge sizes of our galaxies, this most likely won't affect anything inside our immediate neighborhood. Andromeda is 260,000 light years across, while the Milky Way is only about 100,000 light years. And I say only 100,000 light years like it's nothing. But at our highest estimate, our solar system is only about 4 light years in diameter at most. When our galaxy collides with Andromeda, the night sky will be filled with gas clouds and nebulas forming new stars. Assuming there's still life on Earth or in our solar system at this point, because galaxies are mostly empty space, we only need to be worried about avoiding any object within light years. Oh, it may be our own sun. In about 5 billion years, the hydrogen in the sun's core will be completely exhausted and will leave what is called the main sequence, a place where dwarf stars who aren't quite giants live. And this is when the sun will begin to expand, which isn't exactly good for any life on Earth. The Earth, Moon, and according to many scientists, maybe even Mars will be swallowed whole by what is now the red giant sun. But there's an upside. This destruction may cause Titan, one of Saturn's moons, to have conditions extremely similar to what Earth's are today, meaning that we could possibly have living conditions on Titan. But even then, things aren't too safe. Because in the year 22 billion, the first universe-ending scenario comes into play. The Big Rip. Low entropy states require work to achieve, so naturally everything, even on the scale of the universe, seems to tend towards disorder. You can tie this in with the Big Bang. The universe was in an extremely low entropy state in the beginning. All the matter and energy in the entire universe today was compacted down into one minuscule point. Since then, the universe has been expanding, cooling down into a higher entropy state, a more disorderly state. You would think that over the billions of years since the universe's beginning, the universe's expansion would slow down, but actually, it's doing quite the opposite. It's speeding up. This is due to dark energy. We have known that the universe's expansion has been speeding up for decades, but the reason why remained unknown, so we call it dark energy. Right now, the idea is that dark energy will continue expanding the space between galaxies, and that large structures in the universe like galaxies, stars, planets, and even molecular bonds will be strong enough to stay held together. This is due to forces such as gravity and the weak and strong nuclear forces. If this is true, then dark energy will never be able to become strong enough to pull these objects apart. However, there is a possibility that it might not work like that, and this is a problem. There is a bit of experimental evidence that suggests dark energy may get even stronger over time. If this is true, then eventually, in billions of years, the distances between objects won't matter. Anything and everything will be torn apart. First, the galaxies themselves will be ripped apart since the space between objects in a galaxy is so massive, like we talked about with Andromeda. Then, the star systems will be torn apart, our solar system. Then, the stars themselves, and then the planets that even inhabited these solar systems. And if dark energy is strong enough, if it keeps getting stronger and stronger over time, then even objects that are held together by stronger forces, molecular bonds that are held together by the strong and weak nuclear forces, will be shredded apart by the now overpowering dark energy. Nuclei themselves will be ripped apart from their atoms, and this will result in a universe with nothing left. Everything has been ripped apart, down to the very last atom. That is the Big Rip. When dark energy causes space itself to expand faster than the elementary particles that make it up, the universe would just be a sea of empty particles that would never be able to interact with anything ever again. But keep in mind, this is theoretical and based off of only a few scientific experiments. So let's say that doesn't happen. What will happen next? Even if the universe isn't violently ripped apart by dark energy, it still exists. Or at least we think it does. And it is still causing the universe to expand. So by the year 100 billion, dark energy will have caused the entire universe to expand so far apart, even at the speed of light, we won't be able to see or interact with any galaxies that aren't a part of our local group. Out of an entire universe made of hundreds of billions of galaxies, in 100 billion years, we will only be able to interact with a measly 54 of them. And when you do the math, it's kinda sad how little of our universe we'll be able to interact with. In 1 trillion years, these galaxies that we call the local group may collide with one another, back to back to back, until eventually the local group is one mega galaxy. And as cool as that sounds, it's kinda lonely in a way. For any life living in the galaxy, that's it. That's all you'll ever know. And around this time, all the gas clouds that are necessary to form new stars and solar systems will begin to exhaust themselves until eventually there are no new stars being born. All the stars that are alive then will be the last of their kind, until the very last star in the universe fades away into nothingness. And eventually, the universe will go dark, which leads us into our second doomsday event for the universe, the Big Freeze. In 25 trillion years, the last shining star in the universe will either fade out or be swallowed into the supermassive black hole at the center of its galaxy. In 10 to the 30 years, black holes will begin to eat the remaining neutron stars and dwarf stars, while the black holes themselves decay away over trillions of years due to Hawking radiation. In a Google years, that's 10 with 100 zeros after it, a black hole with the size of 20 trillion solar masses, that is a black hole with a mass of over 20 trillion suns, will finally decay completely due to Hawking radiation. And then, there's nothing. In the immense universe over this unreal timescale, there is practically no activity whatsoever. The only activity is random subatomic particles popping into existence for a brief second before they disappear forever like the rest of the universe. That's all there is. The universe has seemed to freeze to a stop. Entropy is at its highest state. The universe is dead. Except, maybe it isn't. In 10 to the 10 to the 10 to the 56 years, which by the way is a number so big that when I sat down and wrote the script for this video, and even now, I couldn't even figure out how to physically write that number down. I tried to figure out a way to put this into scale, but I can't. It's 10 with this many zeros after it, which honestly just makes me more confused. If you were to try and fully write out that number, with all the zeros and everything on one line on a really, really long piece of paper, that piece of paper would be so large that it wouldn't even be able to fit within our observable universe, due to the sheer length of that number. In that many years, due to those subatomic particles we mentioned, combined with quantum tunneling, a phenomenon where particles seemingly instantly teleport between locations, even faster than the speed of light, there is a chance there could somehow be an extreme random entropy decrease at an extremely specific point in the vastness of the universe, where all subatomic particles in the universe quantum tunnel to the same exact location at the same time. This would result in a new Big Bang, a new universe, or maybe new universes.
Most people think of dimensions as directions: left, right, forward and back, up and down, and maybe time as well if we're feeling generous. This framing is comfortable because it preserves the idea that reality is fundamentally stable, and that higher dimensions are simply extensions of what we already know. But that assumption is completely wrong. In the next 30 minutes, you're going to question everything you thought you knew about the universe. With each new dimension that we explore, it'll become clearer to you that the physical laws that bind us are not universal. They're local, conditional, dependent on the fact that we're trapped in the third dimension. But let's not get ahead of ourselves now. To understand higher dimensions, we must first understand the most basic of them, the first and second dimensions. A one-dimensional world is a line. It has length, but nothing else. No width, no depth, no concept of around or beside. The only movement that exists is forward and backward. To trap a one-dimensional object, you only need two lines, one in front and the other behind. That alone completely traps the object. But a two-dimensional object can simply step to the left or the right to escape this prison. In 2 dimensions, we roughly start to see the world as we know it taking shape. Length and width